Hello, and welcome to this lecture on spatial data models. Today, we're going to talk about the second major way in which real-world geographic objects and phenomena can be represented in GIS, which is the raster data model, or more simply, just rasters. If you'll recall from the previous lectures, there are two primary ways in which we can represent and store real-world features as data in GIS. The first way we discussed was the vector data model, which represents features as points, lines, and polygons, along with an attribute table that stores information about the features that we can use for mapping and analysis. In contrast, rasters represent geographic phenomena as continuous grids in which each cell in the grid stores a number. With rasters, there are no points, lines, or polygons, and there is no formal attribute table with fields of data. Data still exists behind the map, but it's stored much differently than it is in the vector model. Despite their differences, both rasters and vectors store data about the real world that is geographically referenced, meaning the features are tied to a specific location on Earth. The vector data model stores coordinates for every point or vertex in a line or polygon, and the raster data model stores that information as a georeferenced grid. In many ways, rasters are actually much simpler to store and conceptualize than vectors, and there are a few fundamental rules that all rasters follow. First, the cells of a raster are always square, with each cell being exactly the same size. The cell size is important because it determines the area on Earth that each cell covers or represents. We refer to the size of the individual cells as the spatial resolution of the raster. For instance, in this example, the size of each side of a single cell in the grid is 10 meters. Therefore, we say that the spatial resolution of this raster is 10 meters. However, it's important to note that the area of each cell is actually 100 square meters because it's 10 meters times 10 meters. Spatial resolution is an important component of the raster data model because it constrains the amount of detail that we can show on the ground. This set of three rasters depicts terrain elevation at three different spatial resolutions: 100 meters, 50 meters, and 25 meters. You can see how the level of detail is much higher or better at the 25-meter raster. We can see all the little nooks and crannies of the terrain that aren't visible on the 100-meter raster. The second important point to note with spatial resolution is that as the resolution decreases by half, the number of cells in the raster increases by 4 times. That means that the storage space needed for higher resolution rasters is much, much higher than for coarse resolution rasters. The second fundamental rule for rasters is that each cell can contain one and only one value or number. In other words, the cells are homogeneous. They cannot store multiple values. This is one of the major ways in which the raster data model is different from the vector data model. If you'll recall, in the vector data model, the attribute table that sits behind the point line or polygon geometry can store hundreds of fields of information. This is not the case with rasters. Each cell can store only one value. On top of that, the value stored in each cell must be numeric. Rasters can represent all sorts of different types of information like elevation, land cover, rainfall, but a numeric code must be used for values that are not naturally numeric. For example, the raster here is storing land cover information for forest, cropland, and water. The values stored in the rasters are numbers, 1, 2, and 3, but those numbers correspond to real-world land cover features. We can color code the numbers to make the map more interpretable, but it's important to realize that the meaning of the values can't be determined simply by looking at the raster. You must have some sort of corresponding legend or table to know that 1 represents forest, 2 represents cropland, and so on. Now, I mentioned earlier that rasters don't have the same sort of attribute table that vectors have. There is a data table associated with the grid, but it only holds a few key pieces of information. When the data are represented by integers, such as in the case we see here, the table will hold those integer values along with a count of the number of cells in the raster with that corresponding value. From this information, you can easily determine the area of each land cover component if you know the spatial resolution of the cell. You simply multiply the cell's area by the count of the number of cells. So for the forest class here, the green one, there are 11 cells. Each of those cells is 100 square meters, which means the total forest area equals 1,100 square meters. If you want to include information about what the various values represent, you'll need to link in a separate table that contains that information. We'll get into these sorts of data table links later on in the class. So to recap, rasters store data as continuous grids where each cell is a square and each cell stores a single number that represents an information value. Rasters differ from vectors in the way they store the geometry of the map and also how they store the data behind the map. We'll begin to work much more with vectors and rasters, so having a solid understanding of their different data models is essential. This concludes our introduction to the raster data model. I will see you next time.